there you go. Well, hope, yeah, I mean, today, yeah, I understand yesterday you probably relaxed a little bit more, but you had to watch some Zoom calls, and you probably kind of liked it because it was a little bit less pressure. You know, you don't have to worry about sitting next to one of your peers, and you could probably, I don't know what you were wearing during the Zoom meetings, and like pajamas or whatever. I really, it was okay if you enjoyed yesterday, but to do that day after day after day after day after day, it really gets old. And so maybe it was good yesterday, but I'm kind of glad it was just a one-day thing. All right, so here's our plan. It's doing the same plan all week. I won't quite finish today. I thought I would almost finish everything today. I won't quite get finished today. And therefore, I will try to wrap it up, everything on Monday. And then Monday, I hopefully have a little bit of time to review. Before you leave today, I know that you have a homework assignment you're supposed to be working on for Chapter 19. I gave that to you a long time ago. And that's something that's due on Tuesday. That's when our test is. But I also have something for you today if you want to use it. It's a practice test that also includes a practice test with hydraulics. The last 2 pages of the chapter have to do with hydraulics. And so if you want to pick that up and say, well, I don't know if I'm going to look at it this weekend, you don't have to. But maybe on Monday, if you get another person you want to study, say, hey, let's do the practice test, including the hydraulics one. Let's see how we do on that. And I did give the answers. So if you want a practice test, you don't have to turn it in. You don't even have to do it. You get it? I'm not trying to give you twice as much work. You already have a lot of homework, right? So I'm not trying to do that. But before you leave today, I want to give you the practice test, which also includes a practice hydraulics question on it too. All right, is everybody okay then? All right, well, good. We should be able to, last period, I think they made some good inroads into this chapter that I think they sort of knew it, but after today, I think they know it better. The only thing I may not get to today, and I'm going to push you a little bit, I'm going to try to get to her hydraulics, and if not, I just have to do it all on Monday. But all right, let's take a look. Before I show you what you should have done on the worksheet, let's go over this again, and just see if it makes sense, because I think these 2 drawings will actually tell you whether or not you might be a little confused. And I don't know, you guys, the basketball players, I know you had the video, and it's not really like being here, but hopefully you watched the video. Maybe you had to watch it more than once or something like that. But I'm going to go over this live, and you guys can ask questions while you're here, okay? But let's see if we can go over this. If this is confusing, that means you probably don't quite understand it. You get it? And I don't want you to take the test and not quite understand it. Let's take a look here. I have a box of water, and it's 1 liter of water. And my question was, what is the volume of water that's in that box? Let's see if we can answer these kind of quickly. What's the volume of water? Go.
Well, your screen's not on it.
What now? Thank you. Thank you very much. Thank you. All right, ready? What's the volume of water in this 1 liter of water? 1 liter. What is the mass of that water? Okay, what is the weight of this water? Okay, so that means the earth is pulling down with a force of 10 newtons. Okay, so I'll draw that vector right there. Now, what used to be in this space here? What used to be in this space? Water. Not the water that was in the box, but water that used to be out here, right? And where is it? It's been displaced. What is the volume of water that's been displaced? What is the volume of water that's been displaced? 1 liter. What is the mass of the water that was been displaced? You gotta go a little faster. 1 kilogram. What is the weight of the water displaced? 10 newtons. And what is the buoyant force on that box? And Archimedes said the buoyant force is equal to the weight of the water displaced. And if 10 newtons of water is displaced, then I should have a 10 Newton buoyant force. Now I'm going to draw that on my diagram also. Buoyant force is always up, weight is always down. Is that correct? Now, be careful. Archimedes' principle is true. This object does have a 10 Newton buoyant force on it, and it's up. But whether or not an object accelerates up, accelerates down, or floats, that's a different question. That's called the principle of flotation. So let's take a look here. If I were to let go of this box, what would happen? I have 10 up and 10 down, no net force. It's going to stay right there, and that's called floating. Whether or not you're floating on top of the water or floating under the water, it's still called floating. Got that? It's called neutrally buoyant. You said you did scuba diving, so did you guys ever talk about go down? I want you to go down 50 feet and become neutrally buoyant. And did you have a BC, what do you call them, BC vest? So a buoyancy compensator vest. Did we talk about that yesterday? BC vest? All right, so in order to go down, you have this tank of air, don't you? Was it a single tank you had? A single tank, okay. And you got all this other equipment on. Now, if you got in the water, would you automatically sink or would you tend to float without your weight belt? Yeah, you tend to float without the weight belt. So they give you a weight belt, and then you would tend to sink, wouldn't you? So what happens is his weight is going to be greater than his buoyant force, and he's going to go down, down, down. But let's say I don't want you to keep going down. So he was yours. How did you operate the CO2 tank? Or what do you CO2?
The buoyancy control.
Yeah,
There's a button that you press.
is a button. Okay, so when you push the button, could you hear the gas coming into the vest? So here's this vest, which is kind of flat to begin with, and he pushes some gas in there. And all of a sudden, he stops going down, and it becomes neutrally buoyant. Now, how did that happen? How does a vest, the carbon dioxide was already with you. You already had that weight. All you did is take the carbon dioxide, put it in the vest, so what happened?
Well, before it was being held in a very small container, it was being compressed. When you allowed to go to the vest, you make it take up a larger space.
Okay, so the way that a life jacket, think about this. You're in the water. Most humans are just a little bit less dense in water, just a little bit. So if you get in the water, some of you, if you keep your chin above the water, some of you will only float that much of you above the water. Get that? And because you're just a little bit less dense in water. So what if you said, I don't like this. I don't like this feeling. Only this much of my body is above water. So I'm going to throw you a life jacket made out of styrofoam. You get it? So you're barely above the water. I'm going to give you something that's going to make you heavier. How is that happening? Why would I give you something that would make you heavier? Have you thought about that? How does a life jacket work? And I think you know, so I'm going to hang on just a minute. I'm going to give you something to make you weigh more. That's supposed to help me? But when I put the life jacket on, I noticed that a large part of my body now is above the water. How does that happen? I want somebody to take a chance and try to explain that. Rollins, you can do that. Let's try it. I'm going to give you a life jacket. Why would that help you? It makes you heavier.
Well, there's less mass per volume.
There's less what?
Mass per volume.
Less mass and volume per what? For the life jacket?
Yeah,
So when I put the life jacket on, what's that do to me total? Less dense. So density is one way to explain that. You're right. My average density now becomes less than it was. But let me ask you this question. What is it that I got a lot out with a life jacket? What do you get a lot of? And you get a lot of something and not very much of another. What is it that when you put a life jacket on, I get a lot of this, but not very much of this? What do you think, Rollins?
more volume and less.
I get a lot of volume that can do what? What can that volume do when it gets in the water? It can displace. It can displace a lot of water. So what does a life jacket do? It gives me a lot of buoyant force. By displacing a lot of water, I get a lot more buoyant force, but it itself doesn't weigh that much more. Yeah, I'm heavier, but I get a lot more buoyant force, don't I? So here's a great question. What if I give you a life jacket, same shape as the styrofoam one, only this one's made out of lead? You put on the lead life jacket. And then you start going down, 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 down. Well, which one gave you more buoyant force? The styrofoam life jacket or the lead life jacket, which is the same size? Which one gave you more buoyant force? I'm looking. Marie, what do you think? Life jacket made out of styrofoam, life jacket same size made out of lead. I put them on, I get in the water. Which one gives me more buoyant force? They would. They would be the same. I don't get it. Then why don't we make life jackets out of lead? Because I get the same amount of buoyant force, but what did the lead jacket do that I don't like? It add a lot of weight. And remember, that's two different stories. Whether or not you sink or float is a different story on whether or not you have Archimedes' principle. You get that? Let's go over here one more time. Here's a 1 liter block of iron, and its density is 8. And so if 1 liter of water weighed 1 kilogram, then 1 liter of iron would weigh 8 kilograms, all right? Now, what used to be in this space right here, a liter of water, which would have a mass of 1 kilogram and a weight of, what would the weight of the displaced water be? 10 newtons. Now, Archimedes says the weight of the water displaced equals the buoyant force. So I have a buoyant force of 10 newtons. Now, that's a different question. So which one of these guys has more buoyant force on it? They have to be the same. But that's a different question as to whether or not you're going to sink or float. You get that? This one's going to remain where it's at, neutrally buoyant. But this one has a weight of 80 newtons, but only a buoyant force of only 10. So a net force is 70 down. You're going to accelerate downwards like that. Here's air. Air is 1,000th the density of water. And so if that was 1 kilogram, this would be 1,000th of a kilogram, and or weigh only 0.01 newtons. So it only weighs 0.01 newtons. But how much buoyant force will 1 liter of air experience? 1 liter of anything underwater will experience how much buoyant force? Anything. How about 1 liter of nothing? How much buoyant force will it have? And look at your faces. What do you think? 10 newtons. So 10 newtons up, 0.01 newtons down. So if I let go of that air thing, it's going to accelerate upwards. Okay, do you understand how you have to separate Archimedes' principle from flotation principle? And this was a great, I thought it was a pretty good question. And both classes missed the first question. 4 blocks equal volume. They're just sitting there right now. Which block has the most buoyant force on it? They're the same size, aren't they? All right. Kieran, help me out. Which one has the most buoyant force on it?
C and D, they're the same.
Right. This one is displacing this much water, and so am I, but you're not. You're only displacing this much water. So less buoyant force. This is the most, less, and even less. Isn't that right? So that's Archimedes' principle. And that's a separate question about why are you down here and why. That's a separate question, isn't it? So if you don't displace very much water, you don't have much buoyant force on you. Ask yourself that question. Look at the bowling ball and the beach ball. Look at the bowling ball and the beach ball. Which one of those has a buoyant force greater than its weight? Which one of those balls? All right, what do you think, Owen?
The beach ball?
All right, what do you think?
Well, actually both.
Wait, you changed your mind.
Actually none of them.
Oh, okay, that's 3 answers. So give me one of those.
None of them.
Which one of those beach balls has a buoyant force greater than its weight?
None of them.
None of them. Otherwise, I'd see the ball going up, wouldn't I? All right, which one of those balls has the greatest amount of buoyant force on it? Who wants to try that one? David.
They have the same amount.
All right, what do you think? What do you think?
All the same size.
Okay, now, that means you didn't understand this yesterday.
Yeah, the bowling.
One more time. Do you see how much water the bowling ball is displacing? Huge! Huge! That means it has a huge buoyant force on it. How much water is the beach ball displacing? Little buoyant force. Who has more buoyant force acting on it? The bowling ball. Separate Archimedes' principle for whether or not something's, all right? If you displace more water, you have more buoyant force on your period. Why is the beach ball only a little bit in the water? What? And the principle of flotation says, when I first put that when I put that bowling ball in there first, weight was greater than buoyant force. And guess what? It went down. And weight was still greater than buoyant force. It went down. And then there was a time when I let go of it and it did that. Why did it stop? Why did it stop going down? When do objects stop sinking? When do they stop sinking? You know,
Buoyant force is equal to the weight.
exactly. So look at the beach ball. How come you only displace a little bit of water? I don't weigh very much. I don't need to displace very much water to equal my weight, right? In which one of those cases is buoyant force equal to the weight? In which ball is buoyant force equal to the weight? Nathan, you know. Yes, both of them. In both of those cases, buoyant force equals weight. Isn't that right? We had a small study group a couple days ago, and I asked them this question, and I want you to think about it. I put you in a swimming pool. That's called fresh water. And you float, and you say, well, here's how much of my body is floating above the water and how much is below. Okay. And then I take you to the ocean. I say, now start floating. And you notice something's different. Then I take you to the Great Salt Lake, which is like 20% salt. And then you notice something different, but you're floating there too. Let me ask you this question. In which case did I have the most buoyant force on me? When I was floating in the freshwater, when I was floating in the ocean, or when I was floating on the Great Salt Lake? Which one did I experience the greatest amount of buoyant force? That's your turn, Sophia. What now? Which one? Freshwater? What do you think? You like that answer? Raise your hand if you like freshwater. If you like the answer freshwater. All right. How many people said she should have said the Great Salt Lake? Raise your hand. How many of you said no, some other answer? I love that. When it was split like that. Okay. What you missed from the story was I was in the freshwater and I was doing what? I was floating. I was in the ocean and I was doing what? I was floating. I was in the Great Salt Lake and I was what? I was floating. In which case did I have the most buoyant force on me? In every case, the buoyant force equaled my weight. The buoyant force was identical all three times. You see that? And I know what your mind's doing. You yelled at the Great Salt Lake, more of your body's above the water. You're right. My body didn't have to displace as much of the salty water to equal my weight. It didn't, did it? I didn't ask you that question. But if I'm floating, in every case, the buoyant force equals my weight. And if I weighed the same, the buoyant force is the same. Is that what you were going to say? Okay. Do you see how this chapter is a little bit more than just sitting here looking at pictures? It's you have to think about it, right? You let it go in your mind like that. Okay. Yes?
What's the reason why saltwater needs to be displaced? Is it because of weight?
Okay, if you displace a liter of fresh water, you'll get about 10 newtons of force, buoyant force, because that's how much that water weighs. But what about a liter of salt water? It's going to weigh more than 10 newtons. So let's say it's 12 newtons. Then for every liter of water, you get 12 newtons. In the Great Salt Lake, it might be 14 newtons, like that. I'm not going to do this to you, but if I had you lay down in liquid mercury, which one would be, and you were floating on mercury, now which one has the greatest amount of buoyant force? It's still the same. But how much of my body would actually be under the mercury? Little bit. Mercury is 13.5 times more dense than water. I wouldn't have to displace hardly any mercury, and I'll be floating on top there, like that. All right. We had, we talked about this the other day, too, in this group. When I first saw this picture many, many years ago, I hadn't been taught like I'm trying to teach you, okay? I had not taught this way. I just, a lot of things I was taught was, here are the facts. Let's have a test on the facts. Okay, now let's do some more facts, all right? I'm not saying that that's not part of school, There's part of school where you have to learn facts. I get it. But to learn how to think about these things, that's what really makes you, I think, intelligent. Some people are really good at recalling facts. They really are. But let's take a look at this. Here's a block of iron, and if I let go of it, it sinks. Here's the same block of iron, except I shape it like that, and it doesn't sink. What's the difference? Who have I called on today? All right, Clay.
You said why does one sink and one doesn't?
What now?
You said why does one sink and one doesn't?
Yeah,
Will they have the same weight, or are we saying they have the same weight?
they do have the same weight.
So they have the same weight, but one of them is taking up much more space, which means it's having a much more water.
You're right. So this one is only displacing this much water, so it gets this much buoyant force. See that? But he weighs quite a bit. So what's going to happen if I let go of it? Weight is greater than buoyant force, and it sinks. Now, this is an interesting question here. If I shape it like this, the ship still weighs the same. It still weighs the same. But what used to be right here? Where is it? It was pushed to the side. It was displaced, wasn't it? And if you push that much water to the side, you're going to get more buoyant force. It's not because the ship has air in it. It's because the water that used to be there has been pushed to the side. So you can't just, let me ask you this question. What if you had a ship and it was in the water and it was at a certain level on the side of the ship, and then I put 5 tons of styrofoam inside the ship? Would the ship sink down lower, or would it ride up higher in the water? So I have a ship and it's empty, and I see where the water level is on the side of the ship, and then I put 5 tons of styrofoam in it. Will the ship rise up higher, or will it sink down lower?
Inside of it, it would sink.
Yeah, in the boat. I'll put it in the boat.
Sink.
What do you think? Mason, what do you think? It would go down. You know why? It's heavier. Yeah, but it's styrofoam. It's heavier. Isn't it? It's heavier. Hey, if you were to build a ship like this, like a V, if you build a ship like a V, that's not good. That's not a good ship. Because if you have this really heavy steel and you make it like a V, you put it in there and you displace only this much water, weight's going to be greater than buoyant force. It's going to go down. And then it goes down here. All right, now I got more buoyant force. Not enough. Not enough. Chances are, if you build a ship like that, you'll never get enough buoyant force to equal your weight. And that ship's going to go down.
Unless you make that.
You know, you always see these videos of the christen a ship, don't they? This huge ship, and they ceremonially, do you really think breaking the bottle is what makes that ship? Really? Think about it. When they break that bottle on the side of the ship, is that enough force to make, really? No. But anyway, they break the bottle on the side, and at the same time, they make sure the ship goes down in this little cradle thing. But what would happen, though, if this huge, huge ship starts going down and then it just keeps going down under the water? If I was an engineer, that would be a nightmare, wouldn't it? I engineered this ship. I did all the math. I know it's going to displace enough water. Uh-oh. What if they christen the ship and it goes under the water? That'd be embarrassing, wouldn't it? Anyway, how in the world can we make a 500,000 Newton ship made out of steel? How can you make it float? How can you make a 500,000 Newton ship float? You design it so it can do what? I know, but how? You design it so it will displace how much? How much? More than what? More than a glass of water? 500,000 newtons. Okay, now if it displaced more than 500,000 newtons, we could do that. But then I'm not sure you could do that. But if I make sure it displaces 500,000 newtons, it will float. It will float. Okay. All right. So I want to show you one more thing, then we'll move on to the last thing. This picture here, it looks like there's not much to learn here, but, but if you look at it, which one of these boats, which one of these cases is the buoyant force the greatest? And somebody said, this class, I know if I don't know the answer, I just say, they're equal. See, is that right? Is that what this is? Which one of these ships right now, which one of these canoes has the greatest amount of buoyant force acting on it? Becca, I haven't talked to you. The what now? Really? Why? Right. See this? This guy here is only displacing this much water. So it only has that much buoyant force on it, right? But this one is displacing a lot of water, and so it gets more buoyant force. Now, that's something to think about is the canoe, when does a canoe stop sinking? When does a canoe stop? What does any object stop sinking when you put it in the water? When buoyant force equals weight. All right, here's that ship thing I was talking about here. We had a another question in that help session I was doing. I thought it was pretty telling. I said we had like a 5-pound lobster, and he was live, and I was on the land, and I put him on a scale. He crawled on the bathroom scale, and it said he weighed 5 pounds. I think I said 10 the other day, but. And then I take the scale, and I zero it underwater, and I let the lobster go, and I put a little piece of food on there, and the lobster crawls on the bathroom scale again. What's it going to read? When it's not in the water, it reads 5 pounds. What's Larry the lobster's weight going to be underwater? What's his apparent weight?
Would it be a lot because all the water is pushing down on the scale?
What do you think? And one of the pictures you had to draw showed that a 1 liter object, even if you take it down further and further, how much buoyant force is acting on it? Even though the pressure gets higher and higher and higher, how much buoyant force is there on a 1 liter object if you take it down? It's still only 10 newtons. And so even though I have a lot of water above me, my volume is what displaces water. And so Larry the lobster's volume is still the same, but he now is underwater. So what does a 5-pound lobster weigh if you put him under apparent weight when you put him underwater? And I'm not coming up with a real number. I just want to know, is it going to be 5, more than 5, or less than 5? You say more than 5 because there's a lot of water pushing down on him. What do you think?
Wait, did you zero out the scale?
Yeah, I had to zero the scale under the water.
Okay.
How did you zero the scale underwater?
I put it underwater, and if it didn't weigh 0, I turn this little knob until it says 0.
Oh, and Larry the lobster's weight would be less
Why is that?
because there's buoyant force acting on it.
That's right. That's right. Next chapter. In the next chapter, I'll ask you this. I have 1 ton of wood, or 1 ton of steel, and it's sitting here. If I were to weigh that thing in a vacuum, would it still weigh 1 ton? This is the next chapter. I have 1 ton of steel sitting in this room. If I were to weigh that thing in a vacuum, would it still weigh 1 ton? Now, you don't have to answer that today because it's actually for next chapter. But what's neat about this chapter and the next, they're both about fluids. And Archimedes' principle is about fluids. That could be liquids or gases. You get that? So believe it or not, right now, I have a buoyant force on me. Why aren't you going up? That's a different question. Right? Am I displacing a fluid? Am I displacing air right now? I am. Then I have a buoyant force on me. Well, how come you're not going up? And without getting too personal, my weight is much greater than the buoyant force. That's why. Oh, I see. So what happens to that 1 ton of steel? That's 1 ton of steel. Let's put it in a vacuum, weigh it again. What's it going to weigh? More than a ton. What? Because when it's in the air, it's being buoyed up, isn't it?
How much is the difference?
But since all of us live not in a vacuum, that's okay. We'll still call it a ton anyway, won't we? We'll call it a ton. What if we go out in space, though? We gotta start thinking about that. How much does it weigh in orbit? Nothing. Okay, well, let's go on. Here's a picture of a ship, and like I said, in World War I and II, they had people who were experts on this, and they had their nice binoculars, and here's somebody come across the Atlantic Ocean. Hey, who is that? Who is that? This is before satellites. Okay. Who is that? I don't know. They're flying this kind of flag, but what kind of ship is it? And they had a book, and all the books had the silhouettes of all the ships, okay? That's one of these ships. Find another page. This ship is designed like this, and that's what spies are for. This ship is designed like this, and we know that it should be about this high in the water. They said that they were carrying food, medical supplies, and bandages and stuff like that. Well, I'm looking at the thing here. It says you should be riding this far down the water because you don't have very much weight in there, do you? We look again and said, Captain, they're way down further in the water than they should be. We're going to go board that ship. Hey, we're going to board your ship. No, we're just carrying food and medical supplies. We're boarding your ship. Oh, no, we don't. No, yes, we are. And what do you find? Tanks, ammunition, heavy things. You get that? How'd you know? See? You were riding much lower in the water than you should. So they've been doing this kind of stuff for a long time. All right. I want to show you the last thing in this chapter. Oh, wait. Okay. This right here is called Pascal's principle, and I'll read it to you. Pascal's principle says that changes in pressure at any point in an enclosed fluid at rest are transmitted undiminished at all points of the fluid in all directions. Wow. If I was your age and I'd say, what are they talking about? So I want you to think about this. What if I had an enclosed fluid? There it is right there. And what if I were to push on this and I say, you know what? I'm going to compress you. And the liquid says, no, you're not. I'm not compressible. But what if I were to put a certain amount of force per area on this piston over here? What would happen? Pascal says in an enclosed fluid, when you apply a force to it, the pressure that you create is distributed everywhere. So whatever pressure is here, it's everywhere. So if I were to put a 1 kilogram mass down here, which is 10 newtons, right, of force, then what could I do over here? What could I lift over here? And I didn't even touch that object. I just put 10 newtons over here, and that guy goes up in the air. Now you might say, that's a waste of time. I could have just gone over and picked it up. But what if we do this? Oh, go ahead.
Is there any inefficiencies?
Oh yeah, now that's getting serious. And I know that you have done a lot of stuff with real engineers. And so you're right, I'm just not scratching the surface. You're right. I do have things like frictional forces and stuff like that. And so if I wanted to make a really efficient one, I'd have to be careful with that. Let's say this is 100% efficient, which you can't do, but I have 10 newtons here. I should be able to lift a 10 Newton object. Even with frictional forces, let's say 10 newtons, I might be able to lift 9.8, maybe 9.8. That's a big point. But watch this. This looks like a waste of time to create Pascal. Come on. Nobody needs your Pascal's principle. But watch what happened. This changed the world. This is one of the things that changed the world. What if I apply a certain amount of force over a small area? So let's make up a number. I hereby declare there's 1 Newton of force here. I hereby declare that that's 1 square centimeter of area. So what's my pressure? My pressure is 1 Newton per square centimeter. Now, what is the pressure right here? What here? Right here, right here, right here, right here, right here, right here, right here. What's the pressure everywhere in this system? 1 Newton per square centimeter, right? But look at this. Small piston, 1 square centimeter. Big piston, 50 square centimeters. What's the pressure? 1 Newton per that square centimeter, and this one, and this one, and this one, and this one, and this one. You push down with 1 Newton of force, and you can lift what? Oh, look at me. 1 square centimeter, 50 square centimeters. 50 times more area. Get that? You put a force of 1 Newton in there, you can lift an object of what? 50 newtons. Wait a minute. It's like magic. That sounds like magic. What if I would 1 and 1,000,000? I could lift 1,000,000 times my force. All simple machines and this operate on the same thing. It's not magic. All simple machines work like this. If you want a machine that makes you put in less force to get a job done, like a lever, you want to use less force, make the job easier for you, you're going to pay a price for that. You're going to pay a price. You might put less force in there, but you better put that force in a bigger distance, right? So I got a lever like this. I'm going to move this rock. Well, this part of the lever will move a large distance, and the rock will move a little distance, but I moved it. I moved that rock, didn't I? It's not magic. You pay a price. You want to use less force? You want to multiply your force? You better be able to multiply your distance. So look what happens here. If I were to push this down, 100 centimeters down, how far up would this go? It's going to multiply my force by 50 times. But I'm going to pay a price for that. If this goes down 100, this will only go up 1. Think about the reciprocal. If I push this down 100, this is only going to go up 1/50th of that distance. What is 1/50th of that distance? 2. I know you're thinking, but think about this. Yeah, I had to put in 100 centimeters to get 2 out. But didn't I multiply my force by 50 times? And so when you see this, nobody really wants to do that. I'm going to lift a car. How are you going to lift a car? I'm going to use hydraulics. By the way, that's what saying. It's called hydraulics. And in this case, I don't want to push a piston down 100 feet to lift a car 10 feet. I don't want to do that. Okay, let's do this then. Let's have your fluid right here, your hydraulic fluid right here. Let's put it in a big tank with some air. And I'll flip a button, and the pump goes on, and goes boom, 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 boom. And what does all this air do for me? What does all the air do for me? Pushes the fluid. It'll push it for me. And my car goes, whoop, 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 whoop. Car goes up in the air. Yes?
Would it go a different amount of distance if there wasn't as much weight on it?
That's a great question. The distance has everything to do with the setup. Now, for example, if this is 50 times the size of that, it'll multiply your force by 50 times, even if you don't put anything on it. I mean, if you only put 1 here, you'll get 50. You put 2 here, you get 100. Now, the same thing happens here with distance. The way it's set up, if it's set up to a 1:50 ratio, it doesn't matter what you put on here, it's still going to be a 1:50 ratio. Remember, because you can't compress a liquid. So if you put an even heavier thing on here, now here's something to think about since you guys are a little bit sharper here. What if I wanted to do this? What if I was willing to put in 50 times the force? Could I get something in return? What if I'm willing to put in 50 times the force, and let's say this piston's way down here, and I'm willing to push this really, really hard, and let's say it moves 2 centimeters in 1 second. It moves 2 centimeters in 1 second. What would this thing do? It would go 100 centimeters in 1 second. You get it? What could I make out of that? A weapon. Couldn't I? Could I push something really, really fast? See, if I put in more force, I get something for that. I get more distance. When you ride a bicycle, how can you ride a bicycle faster than you can run? A bicycle is a simple machine. It's got several simple machines in it. And what you do is you're actually pushing those pedals harder than you need to walk. You're willing to put in more effort, more force, aren't you? what do you get in return? Distance. If my feet go this far in 1 second, the bicycle will go this far in 1 second. And what do you call distance per time? Speed. That's how it works. Anyway, all simple machines are trade-offs between force and distance, like that. All right, I want to show you a couple things here. In your handout sheet, by the way, if you want to pick up a practice test, it also has a practice hydraulics question also. I'll put those back here, okay? All right, let me do 3 quick demonstrations and then we'll be done. Go in your handout sheet and find Cartesian diver number 1. All right, Cartesian diver number 1. This is classic. This bottle here made out of plastic. I used to have one made out of glass. It would have worked with glass, but it got broken, so I said I don't want to do it anymore. And by the way, I found these bottles. And if you know anything about these bottles, anytime you see a bottle this shape, you should know what that means. But if you see a bottle this shape, whether it's made out of metal or glass, it's curved like that. Does anybody know why it's curved like this? Okay, because you can put it in your back pocket, and it's a liquor bottle. Okay, so when you see those things, those little flasks, whether they're made of metal, they have curve because they fit in the back pocket. Anyway, sorry I had to teach that to you. But anyway, this is plastic one. The rubber, the plastic, the glass is all more dense than water. The water is equal to the density of water, and only the air is less dense than water. But the average density of my diver has to be a little bit less than 1, because it's floating a little bit, isn't it? So it's actually less dense than 1. I squeeze on it, watch. I squeeze on it, and it goes down. Now, I did not touch that eyedropper, so how was I able to affect it? Pascal said, if you push on the outside of this enclosed liquid, whatever pressure you create, it's everywhere, everywhere. What's the little bubble of air? What? I just made that bubble of air take up less space. And then only one of these, there's only one thing in here that's compressible. That's the air. Compress air. Now, when the air takes up less space, that leaves a vacuum. What's nature going to do to a vacuum? It's going to fill it in. And there's a hole in the bottom of the hydro. Watch. Water's going in. See? Now what happens? My submarine just got heavier, didn't it? And now weight was greater than buoyant force. This is called Cartesian diver number 1. And the reason I made a dive, I added more weight to my submarine. Weight became greater than buoyant force. Let's go to the next one. Okay, you can stand right here. Stand right here. Don't do anything until I ask you to do it. Ready? This Cartesian diver does not have any open space. Don't do anything yet. What I want to do is try to make these divers go down. So I'm going to ask you, when I say 3, I want you to squeeze it and make the divers go down. 1, 2, 3, go. Okay, good. Okay, good again. One hand. Okay, now, what we're going to do here. Go ahead. 3. Go ahead. Okay, see, wait a minute. What this is called a discrepant event. And what we're doing here, go ahead and sit down. Now, real quickly, what we have here is a different kind of Cartesian diver. And in your handout sheet is Cartesian diver number 2. And there's no open space. But if you think about it, everything in here, the plastic, the metal BBs in there, they're more dense than in water, but there's air in there which is less dense. And again, I'm going to use Pascal's principle and say, I'm going to squeeze you without touching you. Look at the shape of this thing. Look what happens. And what happens is it puckers. Both sides pucker in there. And so what happens is the air in there starts taking up less space, and it makes the water will take up that space on the outside. And so now, how do I increase the density here? Mass stayed the same, but what? Mass stayed the same, but volume went down, so density goes up. Now, thanks for laughing. No, not really. But anyway, what happened is, why was it so easy to make it go down here? This is rubbing alcohol. Rubbing alcohol has a density of about 0.7. It's easier to make something more dense than 0.7 than it is to make it more dense than 1. To make it more dense than 1 with one hand is very difficult. This is the only way I can do it. So I had to really squeeze it to make it more dense. And the last demonstration You'll remember this one. This one, we have a thing here, equal size holes on all of these, like that. And what I'm gonna do is, we're gonna try to compress it. So here we go. Oh, okay, there we go. And what I wanna know is, which one will shoot the water out the furthest? And Pascal says, if I try to compress that water, I'll get equal pressure. I got a leak here. I got equal pressure everywhere. He says that the water should go out in every direction equally. Let's take a look. Ready? Oh, yeah. Okay, so anyway,
This is the best seat in the house.
I didn't get hit last time. Right in my eye. Okay.
I saw you.
All right, see you.
Attention, we are student drivers, and only student drivers can now be dismissed. Lesson will begin in 5 minutes. Teachers, please keep your students in the classroom
Only
until
if you're a student driver.
possible.
You wait. Pick up your practice test if you want one. Yeah. See, you probably thought, oh, what's so hard about that?
Thank you, Mr. Bean.
All right, you're welcome.
Mr. Bean, are we gonna go this Monday with?
Yeah.
Okay.
What happened is, I don't know if I'll do that in class on Monday.
No, I'll find out later.
Oh, yeah, I do that. Let me wipe my hands off. Wait, I gotta stop my video, something I did here.